Hi everyone, thank you for joining this talk. My name is Sêcloka Lazare Guedezounme. I'm a postdoc in the Department of Physics and Astronomy at the University of the Western Cape in South Africa. I am very excited to share some of the work we've been doing on modeling the star formation rate density in counterfactual universes using artificial neural networks. First of all, I would like to thank the organizers of the Multiverse from Home 2025 conference for the opportunity to talk about our work. So let's start. Here is the plan for my talk. In the next few minutes, I will explore how to model star formation rate density, how to use machine learning, specifically artificial neural networks in this context, and present some application. So like the potential implications for the redshift at the star formation rate density peak, for the terrestrial planet formation, and the emergence of life. So here are some important points that motivate our work. We know that the structure and evolution of the universe are deeply influenced by cosmological parameters such as matter density, uh, total matter density, dark energy, curvature, and so on. But what if we change these parameters? So by examining counterfactual universes with varying cosmological parameters, we can better understand the sensitivity of star formation rate density to these parameters. This approach not only enhances our understanding of the universe evolution, but also provide insights into the potential for life in different cosmological settings. So before diving into our methodology, let's clarify some key concepts for this work. Star formation rate density tells us how rapidly stars form per unit volume over cosmic time, and it serves as a proxy for when galaxies emerge, when metallicity rises, and ultimately when planets can form. The star formation rate density is a key metric in cosmology, indicating the rate at which stars form per unit volume. The next concept is counterfactual universes. Counterfactual universes are an ensemble of Lambda CDM universes constructed by taking our own universe as the reference cosmological model and altering one or more key aspects such as the cosmological parameters. So the last concept I want to clarify is artificial neural networks. Artificial neural networks are machine learning algorithms that use interconnected nodes or neurons in a layered structure to process and transmit information. Artificial neural networks learn complex patterns from data, and can be used to solve a wide range of problems, including regression analysis, clustering, um, classification, and so on. Now, what are the objectives of this work? Our, our work aims to achieve several objectives: develop an accurate predictive artificial neural networks model, quantify the sensitivity of star formation rate density to various cosmological parameters, model the evolution of star formation rate density in counterfactual universes, and apply our results to study metallicity evolution, planet formation, and the probability of life in non-fiducial cosmologies. So we consider 6 cosmological parameters defined here: alpha m, alpha lambda, alpha b, alpha k, alpha sigma 8, and alpha ns, defined like this. These parameters represent variation in the energy densities for the total matter, cosmological constants, and baryon, so m, lambda, b, as well as in the curvature, the scalar amplitude and spectral index of the primordial density power spectrum, so K, sigma 8, and NS. To understand and predict star formation rate density in these inverses, we use a semi-analytic model originally developed by these authors, but we extended significantly by allowing all 6 cosmological parameters to vary. Now, to model star formation rate density, we use a skewed Gaussian distribution, which captures not just the amplitude, but also the asymmetry in star formation rates across time. Each star formation rate density curve is parameterized by the amplitude A, by the location mu, the scale or standard deviation sigma, and the skewness alpha. So let's take a look at some example. As you can see, here we have star formation rates density curves for different cosmologies. Each plot shows the star formation rate density data points and their corresponding skew Gaussian density fit for different sets of cosmological parameters. This plot helps us understand how changes in parameters affect the star formation rate density. For instance, with lower matter density, the first plot here, the star formation rate density peaks much later in time, indicating delayed star formation. In contrast, here we have a higher matter, total matter density. The curve This causes the curve to be very sharp and early peaking. So these figures show us how shifts in cosmological structure shape the rhythm of cosmic evolution. But simulating each case individually is computationally intensive. So this leads us to a natural question. Can we train a model to predict the star formation rate density curves directly from cosmological parameters? So it brings us to neural networks. Our artificial neural networks model maps cosmological parameters to star formation rate density characteristics. I mean, the skew Gaussian density parameters. So the input layers takes 6 cosmological parameters, and the output layer predicts the 4 skew Gaussian parameters, then the star formation rate density. So here is just an illustration. In principle, we have 6 neurons or nodes in the input layers and 4 nodes in the output layers. And we have several hidden layers. So we use approximately 5,000 samples, each representing a unique universe with its own set of parameters. We split the data into training, validation, and test data sets to ensure robust training and evaluation. So let me show you how well it's learned. We evaluate our model using learning curves that show the loss and R squared metric over epochs. The loss function is mean square error defined here, and the R squared metric indicates the goodness of fit. So these learning curves demonstrate excellent generalization with the validation loss tracking closely to the training loss, you can see. Same thing for the R squared. So the training loss and the training in R squared are in red, and the validation loss and the validation R squared are in blue, as you can see in the figures. So our model achieves an R squared value of 0.92 on the test data set, demonstrating high predictive accuracy. Moreover, the scatter plots comparing predicted data and actual data for amplitude, scale, mean, and skewness show very tight agreements. So the next thing we investigate is which parameters matter most. Understanding the importance of each cosmological parameters of each cosmological parameter of each fixture helps us identify which parameters must significantly impact the star formation rate density. This analysis reveals that certain parameters have a more substantial influence on the model's predictions. So we use here sharp values. Sharp is a Python package. It is an approach to explain the output of any machine learning model. As we can see here, the blue parts of the bar plots, here the blue is related to the amplitude, the magenta to the sigma, the sigma is the standard deviation, the red is related to the skewness, I mean, and the the green one is related to the location, to the mean. As we can see, alpha B and alpha sigma 8 are more important in the prediction of the amplitude. Alpha sigma 8 and alpha M are more important in the prediction of the standard deviation. Alpha sigma 8 and alpha M have a particular influence on the location prediction and so on. So we can see the varying importance of each cosmological parameters in the prediction of the skew Gaussian distribution parameters. Now, let's talk about some applications. The first is the redshift at the peak of star formation rate density. To compute when peak star formation occurs in each universe, we use the artificial neural networks model to predict the star formation rate density. Then extract the peak time and convert it into a scale factor, and then into a redshift using a modified Friedman equation. As we can see here, if we get the time of star at the peak of star formation rate density, we can get the scale factor at the peak uh, of the star formation rate density, and then the redshift. Here is the modified Friedman equation we use. Each term here at each term here is defined here, and these terms are depend on the cosmological parameters in counterfactual universe, alpha m, alpha lambda, alpha k. So we show here a numerical solution for the scale factor. Particularly, we investigate the effect. It's just an example, the effect of the total matter on the scale factor. So we can see that we can see how different values of matter density shift the scale factor. For high value, universe expands rapidly when alpha m equal 100, and low value slow structure formation when in red here when alpha m equal 0.01. So this diagram summarizes the full process, starting with a set of cosmological parameters, Here we put all the cosmological parameter to the fiducial values, and we vary only one. Here we vary only alpha term. The artificial neural networks predict the star formation rate density shape, from which we extract the peak time and calculate the corresponding redshift. So from this, we get this and we compute this. These plots show the evolution of the redshift at the peak of the star formation rate density as a function of different cosmological parameters compared to our own universe. Each plot illustrates how changes in a specific parameter affect the redshift at the peak of star formation rate density. For example, as alpha sigma 8 varies, the redshift at the peak of star formation rate density changes significantly, indicating the high sensitivity of star formation rate density to the spectral index. For the to the to the not to the spectral index, to the primordial fluctuation amplitude. So for the spectral index, we have um, when the spectral index changes, the redshift at the star formation rate density varies slowly. It's almost close to our own universes. So we can see for the different curve, for the different parameters, the behavior of each of them, the behavior of the redshift at the peak of the star formation rate density when we vary each of them. So the second application, we want to show, but before that, I want to say one thing about these plots. These plots also demonstrate the complex dependencies of star formation rate density on various cosmological parameters, providing insights into the factor that shaped the universe evolutionary history. So now the second application I want to show you is the terrestrial planet formation and the probability of the emergence of life. This plot shows the normalized probability of terrestrial planet formation and the emergence of intelligent life as a function of time for different cosmological parameters. So for example, we can see that when we keep all the cosmological parameters to the fiducial values, to the values of our own universe, and we vary the total matter density, we can see that how the emergence of intelligent life in reds and the terrestrial planet formation. No, I think uh it's a mistake here. The of emergence of life of intelligent life is in blue, not in red. I'm sorry about that. Emergence of intelligent life is in blue, and the terrestrial planet formation is in red. So this will, is just a shift of the maximum of the terrestrial planet formation time to 4.5 gigayears. So we shift this these plots to 4.5 gigayears. And we can see for each plot the effect, the impact of each cosmological parameters has in the terrestrial planet formation and in the emergence of intelligence life. So we can say that this plot provides valuable insights into how different cosmological parameters affect the probability of terrestrial planet formation and the emergence of intelligent life, offering a deeper understanding of the potential for life in various cosmological settings. Now, in conclusion, we model the star formation rate density by a skewed Gaussian distribution. The, we use the powerful tools that is artificial neural network in our modeling to predict star formation rate density in counterfactual universes. Sorry. And we develop an accurate predictive model to quantify parameter sensitivity and explore the implications for planet formation and life. So the future work will extend these models to predict other observables, such as the galaxy mass function, and test more advanced machine learning architectures. So thank you for your attention. I look forward to any question or discussions.